Hello everyone, Mr. John here from Areteem Institute with this week's Thursday Tidbit, where we're going to be talking a little bit about dealing cards and expected value. Now, the inspiration for this video is actually a recent AIME question from this year's, the 2023 AIME I exam. It was number 6 on the exam. Alice knows that 3 red cards and 3 black cards will be revealed to her one at a time in a random order. Before each card is revealed, Alice must guess its color. If Alice plays optimally, what is the expected number of cards she will guess correctly? Now, there's a few things to talk about with this problem. We're going to solve it first, and I'm going to introduce an extension of this question in a sense. This is a question I've asked a lot of the times in previous summer camps and things like that as well, this extension version of it. So I was happy to see something similar show up on this year's AIME test. So a couple of things we want to kind of make sure we're understanding here. First thing, let's deal with this idea of playing optimally. Right? Our question is, well, how should Alice guess there? Right? We know the starting condition, right? We know at the start there are, and let's start using some notation we will introduce at different times and use through different portions of this as well. We know that there are 3 red cards and 3 black cards there. So it's pretty clear at the beginning, it doesn't really matter how Alice guesses. There's 3 red, 3 black. It's a 50-50 chance from there. Well, what about if there's less cards, right? What if we reveal and the first card is red? Well, now there's more black than red. So probably we want to guess black. And you could do this by symmetry in different ways. But as far as we are going to be concerned for today, and a good way to think about this, the guess is, right, as long as the number of red is at least as big as the number of black. So as long as the number of red is at least as big as the number of black, we can guess red. And therefore, okay, if we have more black cards, then we will guess the opposite, things like that there. But just as a baseline, okay, if there's a tie, we guess red. Otherwise, if there's more red, we guess red. If there's more black, we guess black. So that is our kind of optimal strategy here. Now, you can deal with this question directly, but I do want to introduce, and this is a good idea for when you're thinking about problems, both when you're exploring a question for practice. It can really help you understand it better if you try to understand a general version. And especially for more difficult questions, a lot of the times dealing with that actually helps you solve the original problem as well. So rather than just the specific 3 red and 3 black, let's kind of have this general version. Let's define this function where E of RB is the expected number of correct guesses if Alice starts with R red and B black cards there. We'll put this up on the screen again in a second, but we of course want the value of E of 3 and things like that there. So what are some basic properties, or what are some kind of elementary things we can say about E of R and B in this scenario? Now, you could do these things in different orders. Maybe one thing you recognize right away, I already mentioned this word of symmetry, right? If we have the expected number of correct guesses, if you have X red and Y black, this is the same as the expected number if you have Y red and X black, right? It doesn't matter which is red and which is black. So we have this symmetry that's actually going to help us out a lot in the second that we have here as well. And then just to be complete, let me write this out in two versions. However, based on this first symmetry property, we don't need both of these. But just so we kind of have it, maybe you would be starting here as well. It should be fairly clear. If we know we're down to only red cards, Alice should be able to get every guess correct. Remember, we're always assuming that we know the cards that we start with, and therefore once we know when cards are revealed, we know how many are left. So if there's only red cards left, Alice can guess red the rest of the way, or if there's only black cards left, Alice can guess black the rest of the way as well. So we have these base cases or things like that there. And you probably see where we're going with this here. We talk about some symmetry. Now let's say, well, we have what happens when 0 is left from a card. A natural thing might be to try to build things up. You might look for a pattern. You might look for other values there. In fact, we can have a very nice recurrence. Or, right, another word for this is you could call this a recursive formula. Things like that as well. So a recurrence, recursive formula. If you were actually programming this, this is a formula you could use in some sort of dynamic programming, it may be called recursive programming, things like that as well. Now, right off the bat, just to help us out, one of the reasons we talked about symmetry is remember then that we can assume for the equation that we're going to write out here that the number of red is greater than or equal to the number of black. Otherwise, flip things around, it works the same the other direction as well. But that'll just clean stuff up here, and it also makes it a little bit easier to explain because we now know for sure that the guess is red. We can assume there's more red cards, so our guess is red in that case. So, what can we do here? Well, the expected number if we have R and B, right? And if you want to picture this in a tree diagram and things like that as well, it can oftentimes be helpful to draw out that picture. Where we are, the next card can either be red or black. Right? And then we're left in scenarios where we have one less red card or one less black card left over at the end of that there. And this diagram helps us come up with our formula that we want. So for example, if we have R red cards and B black cards, what is the probability that we go down this red path? We go down this path with a probability of R over R plus B. Now, our guess is red, so this time we have a correct guess. And then we are in the recursive scenario where we have one less red card, the same number of black cards there. So this is our setup here going down this first path in that scenario. So this is that first branch, if you like, of this tree down here. And if you're first learning about this stuff, I really recommend drawing out these diagrams. They can really help you picture what's going on in this scenario. Because our second scenario here, right, is, okay, what's the probability we pick a black card? Well, it's 1 minus that. It's the complement. Here, our guess is incorrect, so we don't get any correct guesses from that round, but we still get however many guesses from the remaining B minus 1 black cards and R red cards that we have left. So we have this pretty nice recurrence there, right? And formula looks a little bit confusing, but remember in terms of these branches, we're going to write out not all of them and show all of the work, but a few of them, and it'll be helpful on the next slide. Oh, what's the probability of red? you get a guess correct, smaller case. What's the probability of black? You don't get it correct, smaller case. And when we start working through things like that, that's going to be helpful in that scenario there as well. Okay, so let's look at how we could use this recurrence and those basic properties that we talked about on the previous slide there to actually build up to E of 3, 3, right? Remember, this is the actual AIME question. This was our AIME problem here. What is E of 3, 3? Of course, on the actual AIME exam this week, you had to deal with what's the fraction and numerator and denominator. We're ignoring that stuff and just calculating the actual value in this case. So let's start building this up. So what happens if we just have one card? And I'm going to do a few of these with a little bit more detail, and then I'll give you the values so you can double check stuff. But one red, one black. So we're guessing red. There's a half chance we're correct. And then just so we start seeing the recurrence, there is one less card left. There's a 1/2 chance our guess is wrong. And then we have only one card left. It is now a red card in this scenario. Whoops. So I need to switch my numbers around here. It actually wouldn't change our answer in this case, but we have 0, 1, 0 in that scenario there. So 1/2 chance times, well, anytime there's one card left, right? Actually, both of these values here, anytime there's one or only one type of card left, we know that value is just however many cards there are. 1/2 times 1 plus 1 plus 1/2 times 1. I guess let me write this out. So 1/2 times 2 plus 1/2 times 1. We have enough room here, and we have that is 3/2 in this scenario. Now, a little bit tedious, and this is why I'm going to skip some of the steps along the way, but let's write out a few more of these, right? So what about E of 2, 1 there? Just to remember, now we have 2 red, 1 black. So if we're guessing red, we now have a 2/3 chance that we got a guess correct, and now there is one less red card available to us. There's a 1/3 chance our guess is incorrect, so we didn't get it correct. Now, however, we got rid of the 1 black card, so this is E of 2, 0 in this case. Let's do this one just verbally here. So E of 1, 1 is 3/2, so we have 2/3 times 1 plus 3/2 plus 1/3 times 0 plus 2. And if you calculate this out here, this is going to give us 7/3 in this scenario. Quick reminder, remember that this is also equal to, right? We can, just for reference here, this is the same as E of 1, 2. Remember, we have that symmetry going on to help us out there as well. And now you can start seeing how these are built up. So just because I want to write one more example out, let's do the 2, 2 case. So here we have 1 plus E of 2, 1 with a 1/2 chance. We have a 1/2 chance of getting it incorrect, 0 plus E of 2, 1. Or sorry, 1, 2 in that case. And for some reason, I always want to mess up these there. Again, the order doesn't really matter. I think that's why I keep messing it up in this case. And then in this scenario, when you simplify it out, you get 17/6. And hopefully it's pretty clear from here that this strategy, you just have some busy work, but it's very easy. AIME, you do have a lot of time to solve the questions, so I'm going to skip writing out the formulas, but using this same exact strategy, you will find that E of 3, 1 is the same as E of 1, 3 is 13 over 4, right? Just in case you want to double check some of these things, E of 3, 2 is the same as E of 2, 3 is equal to 18 over 5. And all of this is getting us to the punchline of now we would have everything we need to calculate E of 3, 3, and you will get 41 over 10 in that scenario there. So that would be our final answer. That is the answer to the AIME problem up to turning it into the AIME format that we would like there. Okay, so here we were talking about the expected value of the number of guesses AIME got correct. And in our questions for next week, I want to introduce the idea of betting on the next card. So our question 1 is the pretty simple version. Alice starts with $1. She now bets on the outcome of each card. So before the first card, she could, instead of guessing red or black, she would bet her money. So the first card, she would bet whether it's red or it's black. If she wins her bet, she doubles her money. If she loses her bet, she of course loses that money. So in the first question, this is pretty similar. Using the same strategy, that still makes sense. If you're forced to bet all your money each round, you probably want to bet however many cards there are more of. What is the expected amount of money she ends up with there? So it's very, very similar to the previous scenario. Here, however, you're losing all of your money, right? So as a little bit of a hint, for example, if there's 4 cards, in this scenario, either Alice ends up with $16, right? She starts with $1, that would go to 2, 4, 8, 16, right? She would double her money in every one of the 4 bets, or she would end up with nothing, right? There's a possibility if she's betting all of her money each round, she could end up with nothing. And it's very similar to the AIME problem, but here then let's try to figure out the expected amount of money Alice ends up with for some small values of N red and N black cards. So very similar to what we did. What if we have 2 red, 2 black, 1 red, 1 black, 3 red, 3 black, things like that there. Now, the real question, the interesting question here, is we can turn this into a guarantee, actually. That's a little bit of a spoiler, but that's okay. Suppose now that Alice does not necessarily bet all of her money each round there. So, right, just as a quick example here, right? For example, if N equals 1, right? If we have 1 red, 1 black, right? We can, on the first card, right? We can have no bet, or let me say we bet $0, right? I don't want to risk anything there. What's the advantage of this? Well, then for the second card, we automatically win, right? We still know the cards. So if there's 2 cards, I want to see the first one, and then I can double my money, right? And we end with $2. And this strategy is a guarantee. With this strategy, I always can win $2 if we start with 1 red and black card. Right? Try to, right? And just to make it clear, you can bet none of your money, all of your money, a fraction of the money. It doesn't need to make sense with cents, right? So if you have $1, we're assuming she can bet 1/3 of $1 or 1/5 of $1, things like that there. And the question is, right, can you come up with a betting strategy that guarantees Alice will win the amount of money based on what you came up in question 1. So we just came up with a strategy that she can always win $2 if there's one card, one red, one black card. Right? So try to explore different things there, and the key, however, is no matter what happens, right? When we're talking about expected value in question 1, that's up to chance. Sometimes she wins a lot of money, a lot of the times she wins no money, right? Here then we want to say, can you come up with a strategy where you're not risking it all, right? The problem with risking it all is that once you lose it, you can never win it back. Here, maybe you save some money for later bets. Can you come up with this strategy to always guarantee you win some amount of money there? So that's going to do it for this week's video. We're going to continue talking about this question next week. So if you have thoughts about this question, share in the comments below. Please like this video, subscribe to the channel for new updates and a new video each week. Otherwise, thank you all for watching, and I'll see you next time. Goodbye.